Okay, so today we're going to be doing improper integrals. An improper integral is, as it says up here, an integral where either the interval is indefinite or the function itself has an indefinite discontinuity on the interval. So the first kind is the infinite interval, which means that the interval of your integral keeps on going and going forever. This integral right here, it helps if I select a color, there we go. It means that we're looking at the area underneath the curve of 1 over x squared from 1 all the way on up until infinity. To get a better idea of that, I'm going to go ahead and graph it real quick. So let's see, let's make this right here 1, this will be a 2, we've got a 1, and we've got a 2. So if I graph the 1 over x squared function, we plug in a 1, we get out a 1, plug in a 2, we get out a 1/4, and then we're going to have another one up over here. So if we connect those, okay, so what we're actually looking at is the area underneath this curve from 1 on forward forever. The big question is whether the area underneath a curve like that can be a finite number, and it turns out that sometimes it can. To figure out the answer, we have to do a couple steps in the middle, but first I need you to know a little bit of terminology that we're going to use a whole lot second semester. If the area is infinitely large, then we say that the integral is divergent. And that's the phrase that we're going to use a lot second semester. We're going to go ahead and figure out whether or not this particular integral is divergent or whether it has an actual finite number as a value. So our first thing we do, as it says over here on the side, is we write the integral itself as a limit. Since we can't technically plug in an infinity, we think of it as the limit as pick some variable. The book uses t a lot, so I go ahead and do that also. The t is going to be our infinity. And then we replace our infinity up here with a t itself. Everything else stays the same. So I just wrote it as a limit. Then you integrate. So the integral of 1 over x squared, remember it helps to think of that as x to the negative 2. So if you integrate x to the negative 2, that turns into a negative x to the negative 1. So we have the limit as t approaches infinity of, I'm going to write that x to the negative 1 as a negative 1 over x. And this is really important, as I said last class, when you're evaluating limits, to think of negative exponents as fractions. You're much less prone to making small mistakes inside the process. So we have a negative 1 over x. We're evaluating that from 1 to t. Okay, that was our integrate, whoop, right here. Last thing we do is we evaluate the integral. To evaluate the integral, we start by plugging that t in, which means we're actually going to take the limit as t approaches infinity of negative 1 over t. That's the first piece. Then we're going to minus off what we got when we plugged the 1 in, which is a negative 1 over 1. When you plug an infinity in into this first part over here, negative 1 over some massive number ends up just being 0. And then the second piece is a positive 1, so the answer to this is 1. Which means that if you hop back to our graph, if we look at the area underneath this curve on toward infinity, that the area is actually approaching a finite number. If you use like a Riemann sum type situation and you added up all those tiny boxes and you kept adding until the end of time, it's going to approach 1, which I think is kind of cool. So our answer is 1. We don't always get a finite answer, and I want to show you a couple different ways of doing these. So a couple more examples. You won't always have a positive infinity. Sometimes you'll have a negative infinity, like this first example here. Same process, though. Start by writing it as a limit. And this may seem tedious, but the AP exam often has this type of a problem embedded in a free response, so you need to know how to write it the way that they want. So we go limit t approaches a negative infinity this time. we're going from t to 0 of 1 over 2x minus 5 dx. Then we integrate. So the integral of that, remember all of our partial fraction stuff from earlier? We'll do a little u substitution in our head, which means the du is going to be a 2 dx. We're going to need an extra half, but we're going to get lots of natural logs when we have things like this. So the limit as t goes to a negative infinity, we're going to have a 1/2 natural log absolute value of 2x minus 5 from t to 0. So that's us evaluating the integral. Or excuse me, that's us actually integrating. After we integrate, we evaluate. I'm going to move this little guy down here out of the way. So to evaluate, we plug the 0 in first. So we end up with a 1/2 natural log of the absolute value of a negative 5. That's the first piece. Then when we plug the t in, we really have to do the limit as t approaches negative infinity, 1/2 natural log 2t minus 5. So when you do this, if you think of the infinity being in there, we're really taking the natural log of infinity, because we take the absolute value. So what happens to the natural log graph as you go on and on and on toward infinity? We end up with an infinite answer. So this little guy needs to go further out of the way. The first piece was a 1/2 natural log of 5, but we're going to subtract off an infinity. So is 1/2 the natural log of 5 minus infinity a finite answer or an infinite answer? It is definitely infinite, so what we say is that our integral is divergent. It certainly does not approach a finite area. So that's the answer to that one. Okay, another example, this type right here. Start same process in the beginning, write it as a limit. So we go from 1 to t, 3x plus 1, quantity squared. Okay, this is where it comes in handy doing those quick, fast integrals in your head. Show this stuff if you want. If you don't, fabulous. We're going to do u substitution. U equals 3x plus 1. The du is going to be 3. So when we integrate that, we're going to end up with we're going to actually integrate 1 over u squared, which is u to the negative 2. So we're going to end up with a negative 1 over u, which was the 3x plus 1. But don't forget this 3 right here. We're going to need a third to take care of that. So I'm going to stick him right here. We're evaluating that from 1 to t. Plug in our bounds, which means we're going to end up with the limit t goes to infinity, negative 1 over, I'm going to distribute that, 9t plus 3. That's the first part. Minus off. Plug the 1 into that whole thing, so we get a negative 1 over 3 times 1 is 3 plus 1 is 4. We get 12. Taking the limit of the first part, 9 times infinity plus 3, massive bottom, gives us 0 plus 1/12. So our answer is 1/12. So we can say that this integral has a finite area underneath the curve if we're looking from 1 on to infinity. And that area is going to approach 1/12. I keep wanting to ask you guys if you have questions, but there's nobody here. Okay. This kind of a problem, if you have infinities on both sides, if you're going from a negative infinity to a positive infinity, we split it into 2 pieces. Doesn't really matter how you split it. Usually I split it 0. The good thing to know, as it says on the side here, is that if either of the pieces diverges, then the whole thing diverges. We know back from Calc AB that if you have an integral like this, we can go the integral from a negative infinity to any number. I like to pick 0, like I said, of 1 plus x squared dx. We can take that and add on the area from the rest of the curve, and we get the area of the whole thing. There we go. So writing it as a limit, I admit that I sometimes get totally lazy and I don't write every single one of them. And on your homework and on your Well, I want you to do them right on the concept quizzes. But on your homework, I don't mind if you skip the writing it as a limit part. But make sure that you think it and that you know it. I will check it on quizzes because I need you to show me that you can write it that way. So what I tend to do for myself is at this point go, okay, what is the integral of 1 over 1 plus x squared? I hope absolutely everybody remembers that that is arctangent. It's been on our memorization quiz forever. And we're going from negative infinity to 0. And the other integral is the exact same thing, so we don't have to do it again. This is from 0 to positive infinity. So plug in our bounds. Arctangent of 0. When is tangent 0? Tangent is 0 at 0. Minus arctangent of negative infinity. So if you imagine the unit circle, that's talking about when the slope of that line, the sine over the cosine, is equal to a negative infinity, which is down at a negative pi over 2. So that's the first piece. Second piece, arctangent of positive infinity. Same idea. I imagine in my head a unit circle, and I think, oh, that's up at pi over 2. And arctangent of 0, we already decided was 0. So we take those two fellows. We got a positive pi over 2 and another positive pi over 2. So we get pi, which is kind of a fun answer. So the area underneath that curve from negative infinity to positive infinity is pi. That is the first kind of improper integral where you have an infinite interval. They aren't all like that also, or excuse me, however. There's also kinds that have discontinuous integrands. So here's a couple examples. Discontinuous integrands means that basically there's an issue or a problem on the interval that we're taking the integral on. So if our function or our curve is 1 over the square root of x minus 2, we have a problem at, let me erase my little pen mark there. We have a problem at 2 itself. If we plug a 2 in, our curve is undefined, so it's an infinite discontinuity on there somewhere. We treat it the exact same way as the good news. You would start by writing it as a limit, since we can't technically plug a 2 into that function. We use the t again. And we're going to go from t to 5. Our equation is 1 over the square root of x minus 2 dx. Then we go ahead and integrate, so same process as before. U is equal to x minus 2. The du is just dx. So we end up, we're really integrating a u to the negative 1/2. I'm just going to jot that on the side because it makes it a little bit easier to think about it. When you integrate, you add and you divide, so we end up with a 2 u to the 1/2. Since our u is x minus 2, 1/2. And we're going from t to 5, and this was a limit as t approaches 2. So again, I wrote it as a limit, I actually integrated, and the last thing we do is evaluate the integral. Move him out of the way. So to evaluate, we need to plug in our bounds. When we put the 5 in, we end up 2 times 5 minus 2 is 3, square root of 3. When we put the 2 in now, which we technically can plug in, we end up with 2 times 0, which is just 0. So our answer is 2 square root of 3. So same process, you wait to evaluate the limit at the end, but you just have to think of the problem as a limit problem. Oops, my examples are getting all squished together. More space. Okay, so I'm going to more quickly go through these. I want to get you guys some just sheer exposure to lots of them. Again, I'm not going to write that limit step all the time, but remember you need to on the quiz. Where is the problem on this one? It's not at 0, it's not at 3, but our denominator is an x minus 1, which means that this is going to have domain problems at 1 itself. When this happens, you need to take your integral and split it at the point that's discontinuous. So we're going to write this as the integral from 0 to 1 of dx over x minus 1 plus the integral from 1 to 3. So let me say that one more time so it's a little bit low. That was ugly. Ah. There we go. So this very first example that we did, one of the endpoints of our interval was a point of discontinuity. On the second example, a point of discontinuity was in the middle of the interval. When that happens, you take your integral and you split it into two pieces, right at the point of discontinuity. And then you continue just like all the other problems. So you should write it with a limit at the 1. I'm going to skip that step. When you integrate the dx over x minus 1, we end up with natural logs. So you have the natural log of x minus 1. We're going to evaluate, oops, I need another line there. We're going to evaluate from 0 to 1. Excuse me. And same thing on this side. Natural log of x minus 1 from 1 to 3. We'll log them in. So if we put a 1 in, we have natural log of 0. If you imagine your natural log graph, as you approach 0, our natural log is going to end up a negative infinity. So I'm going to stop right there. Does it matter what else is happening in this problem? I'm going to tell you it kind of does. You need to make sure you don't end up with an indeterminate in the middle of evaluating your integral. So I'm just going to continue evaluating the first piece. When I plug the 0 in now, we're going to have the natural log of 0 minus 1. So that's the natural log of 1, which is 0. So when I did just the first integral, I ended up with a negative infinity minus 0, which is certainly not a finite number. That means I don't even have to finish the rest of the problem. I can just ignore it. It doesn't matter what I add to an infinite area. My answer is still going to be something infinitely huge. So we say that it is divergent. And that is our answer. Okay, one more of these. Move him down. Excuse me. When you integrate natural log of x dx, I threw this example in here because it's a good one to remember how to integrate, for one. Where is our area of discontinuity? The graph of natural log has a discontinuity at 0, so it's not in the middle of the interval. We would write it as a limit, with 0 being a little problem child right there. To evaluate the integral, we don't know the integral of natural log of x, so we do integration by parts. When you have a natural log like this, you always make the u equal to the natural log piece, even though that doesn't go to 0 as we differentiate. The dv piece is going to be the dx. So this is a review of what we did in the first section. Derivative natural log is 1 over x dx. Integral of dv, so our v is going to be x dx. I always like to put these guys in their own little box. That means we can rewrite our integral. 0 didn't turn up. There we go. As uv minus the integral of v du. So uv is going to be an x ln x. Oops, I have extra dx's going on over here. Go away. So uv is x ln x minus the integral of v du. So that's going to be x times 1 over x dx. Simplify that a little bit. We get x ln x minus, that's really just integrating 1. Integral of 1 is x. X. Okay, notice I completely ignored the bounds throughout this entire process. I tend to do that because it's easier just to stick them back on in the end. So I'm going to do that. Now I go ahead and plug them in. When I plug a 1 in, we have 1 times natural log of 1 minus 1. We plug a 0 in, we get 0 times natural log of 0 minus 0. What does that make? So the natural log of 1 is 0. Okay, so this whole thing right here is a negative 1. The second piece, natural log of 0. Can't do that. We get that negative infinity again. So, doesn't really matter what else is going on. Let's see if I can make a few stars. Can't make stars right now. There we go. Yay! As soon as we see that infinity, doesn't matter what we're adding or subtracting, it means that our answer is divergent. Doo-doo-doo. So, those are your homework problems. It's on the website. Answers are on the website. I will go over any questions you guys have on Thursday when I get back. And these notes that I just did, I know I went super fast. They are also on the website if you want to print them off, put them on your iPads to look at, excuse me. And that is everything. I hope all this made sense. I will go over questions.